There was snow going horizontally, big white caps and ice everywhere. It was terrifying. So here's what's interesting about Guth's model. There's some parameters you have to put in. You get to turn some knobs. And if he turns the knobs just right, he matches the data. One of the knobs he turns is how much atomic material is there in the universe. And you turn that knob to help you get to your theory to match the data, and he gets an extraordinary result. He gets this wedge of this is the entire universe. The theory shows us that dark energy makes up most of the energy in the universe. That's the energy that's making the expansion accelerate. And the more it expands, the more room there is for dark energy. We don't know what it is, but it just appears spontaneously, and it makes the universe expand even faster. His results that match the data say 68% of the energy in the universe is dark energy. Nobody knows what it is. He also gets that 32%, that's what's left, of the energy in the universe is matter of some form. And of that matter, the part that's made of atoms like us and stars and galaxies is 5% of the energy in the universe. So I'm relying on you knowing the famous equation that energy and mass are related. You might have seen that around. So this is a picture, this is a family picture of all the energy in the universe. And 5% of it is the stuff we're made of. The rest of it, we don't know what it is. If you turn the knobs, you get this result. But he's not the only one turning knobs, as we shall see. See how we're doing tonight. We also have the modern version of what Alpher and Gamow did, and that is Big Bang nucleosynthesis. And I have shown this before, and what it says is we have, depending on how much matter is in the universe, that's what this scale is, we have models of how much hydrogen, helium, lithium, and so forth should be observed by astronomers. And you can slide this bar, this vertical gray bar tells us where we have the best match between measurement and theory. And it turns out right at around 4% for the atomic matter in the universe. So Guth's model and the Big Bang nucleosynthesis model give us the same result, that about 5% of the universe is atomic stuff like us and stars and galaxies, and the rest of it we don't know what it is. And that matches what we observe if we measure the amount of deuterium, lithium, helium, and other elements. It's a very successful theory, but only if the universe is 5% atoms. And that's not all. That's why I circled this right here. This is a little thing about, there's an issue with neutrons that we will not, let's not get distracted right now. It turns out the neutron problem is more complicated than we thought. Remember I said the early universe was depleted of neutrons. I actually showed this drawing before. There's something else going on there. Now, this is where it all comes together, concordance. So, from the cosmic microwave background, the distribution of the hot and cold areas, we know that about 5% of the total matter/energy, that's why matter/energy, there they are related, of all the energy and matter in the universe, 5% is atoms. There's that picture I just showed you. There's the same result from Big Bang nucleosynthesis. So that's just a recap. Now this is really important. This is the so-called concordance. What we're plotting here is how much of the universe is mass. Remember, there's generally two kinds of things that we can have, mass and light. So here's how much mass we might exist in the universe, and vertically is how much of the universe is dark energy. And here's what we see. Here's the cosmic microwave background data, this orange slice. And it says, well, we are uncertain. The dark energy could be this big or this low, but it's got to be somewhere in this wedge. Then we have something else, which I hope we'll get to today, which is called baryon acoustic oscillations, which is the noise in the early universe, which affected how the hot and cold spots are placed, how we observe them. And that's this green slice. Completely different. These are completely different teams working on completely different data. So we have the orange slice and we have the green slice, and they do intersect kind of in this neighborhood. And in this, supernova explosion data. And that also intersects right here. Now let's go to the next page. So now we're zoomed in. Now we're looking at, here's how much mass is in the universe. A large part of that mass is dark matter. We don't know what it is. But the total mass in the universe looks like, based on this, it's kind of like 30%. In fact, I think I have a little meatball. Yes. That looks like where the most probable point is, like 32% matter, total matter. Now let me interrupt myself and back up here. That means we've added these two together. Atoms and whatever else that other stuff is. If we look at this and put that little meatball there, that says the best match is that 32% of the matter in the universe and about 68% of the universe is dark energy. And this comes from multiple different independent techniques for measurement. And they all agree. Oh, and this, by the way, the blue area, this little blue thing, which is really very precise about what it's saying, this comes from looking at the combination of the cosmic microwave background data and how light is bent by stars and galaxies. And that, look how small that little ellipse is. If we go back to the prior page, we're looking at this little area here. So once again, we're homing in on this idea that 68% of the universe is red, right off of this scale. If we go right over there, that's 68%. That's how much is dark energy. And the total matter is the combination of these two slices, 32%. Now you can go in even farther. So here we have, this is the name of an experiment that looks at supernova events. This adds Big Bang nucleosynthesis by doing precise measurements of how much lithium, boron, carbon, uranium, and stuff we see in the universe. And now we're really zoomed in, and we're right down. I did not draw this. Actual professionals drew this, and we're right at about 32% matter and 68%. Oh, and this is 32% matter, and this implies the expansion rate of the universe, the Hubble constant. So this data, which led to a Nobel Prize, says the expansion rate has this number of 68. I think in our first conversation we talked about there's a problem. Because this data just doesn't agree with other techniques. So we're not done yet. But when you look at this, we have high precision about the distribution of matter and energy in the universe. So now let's talk about acoustic oscillations. So the idea is, here is the distribution of the little lady in my watch wants to hook to the Wi-Fi, so I have to wait. So here's cosmic microwave background. And from this, we can predict the clumpiness that we should see in galaxies. I said this earlier, like right before the break, that this distribution of hot and cold spots implies where we should see concentrations of galaxies or voids. And people have done this. And what they find is, and the way they do this, they're looking for coincidence between the distribution of galaxies and the distribution of temperature. And they get this bump. This is highly technical stuff, but this bump represents an echo in how sound was propagating in the early universe. And when you have echoes, let's talk about what goes on when I'm speaking to you or you're speaking to someone else. The sound waves change the density of air as they propagate. And when they arrive at your ear, the pressure in your ear changes in a microscopic way, and you sense that. This is the same kind of thing, that we have a bump right here that indicates that the correlation between temperature distribution in the very early universe, remember, this is from 380,000 years after the bang. This is 13 billion years old, this light. And the galaxies that we see are of different ages, but many of them are much less than 13 billion years. We look at galaxies all the time that are less than 1 billion years old, or hundreds of millions of years old. So the whole universe has expanded this way, and there's a bump indicating that there's an acoustic correlation. That is, sound waves in the early universe dictated where the galaxies were going to form. If that were not true, this curve would have gone down. The purple shows what would have happened. If there was no bump there, they'd say there's no correlation between temperature and where the galaxies appear. But it's there. So we have this, I already showed you this. That's the concordance. Now there's additional information, and it comes from the supernova data, and that is this clumping of these. This is, each dot is a different supernova measuring its position and its velocity. And this clumping that is up here in this part of the drawing indicates that the universe expansion rate is accelerating. It's getting bigger. In fact, any evidence of an accelerating expansion rate would be implied if all these red dots were right along this line. And they are pretty close. That is, the average sits right on that line. That led to a Nobel Prize. And from that, you get this estimate for the amount of matter and energy, dark energy in the universe. You get the same numbers that we get from the cosmic microwave background. Does that mean we really understand what's going on? No, but it's very suggestive that multiple different techniques are giving us the same number. This one shows a little difference, 28% matter, not 32. And from cosmic microwave background, we got 68% dark energy. We got 72 here. Still pretty close together. I don't think I'm going to talk about that. And this is that's a picture of a supernova remnant. Nobel Prize for these guys. They're under some pressure now because there's this recent disagreement between different techniques in measuring the Hubble constant, which I talked about in the first lecture. But the best data we have from Planck, and here's WMAP says 0.72 and 28. Planck with some other data gives this. Planck. So you can see there's different experiments. They're all orbiting around the same thing. So let's talk about what these bumps mean. Remember, I showed you this. Sorry, I'm just checking time. Here's the cosmic microwave background. And this peak represents the first acoustic compression of sound in the early universe. So there was a sound wave propagated, just like my voice propagating through air, get to you. Sound propagating through the atmosphere compressed the whatever was there as the sound wave went by. In the universe, a simple way to describe it is that's like a ripple on the surface of a balloon. If that ripple is propagating, it's going to come back around. And it does. And that's what this bump is. This is remember we get pressure. When a sound wave goes by, there's some pressure, and then the pressure goes down, and then the pressure comes up. This is the peak pressurization, and then we have, this one is the stretching that causes the pressure to go down. And then we see the next bump, and the next bump, and the next bump. So the fact that the cosmic microwave background, when analyzed to produce, sorry, don't get dizzy, to get this, these bumps are associated with acoustics in the early universe, keeping in mind the complexity that as the sound waves are propagating, the universe is getting bigger. So it means that, let's use the balloon analogy again. If I have a ripple moving on the surface of a balloon, and while it's moving, the balloon is getting bigger, that means when that deformation reappears, it will have been stretched. So its size will be different. And that's what we're seeing here. So sound waves in the early universe. And there's a guy, University of Virginia. Oh, okay, so here's a cartoon, and I'll tell you about Virginia. So we got, this looks like a whistle. I'm not exactly sure what this is supposed to look like, a police or an athletic whistle. So we have a peak of pressure, and then we have a minimum of pressure, and so forth. And the second time around, we get these overtones. Any of you who are musicians know about this. We all can tell the difference between a piano playing a note and a violin playing a note. There's complexity in the overtones. And that's what happened here in the early universe. We have a hot area and a cold area, and here's the cold region the hot region propagating this way. That means this blue is now over here, and so temperature is propagating along with sound waves. So now, Pam,
It should be set up okay.
you ready to cover your ears. So I'm just going to play a standard tone. Was that too loud for people? Like, if you have hearing aids or something, let me know and we'll fix it. Now we're gonna go here. I don't know why that happened. That's inconvenient. All right, we know what to do. So this guy at the University of Virginia studies sound waves in the early universe. And here's what he finds. Now, once again, this is the cosmic microwave background implying what the frequencies are. Instead of hearing 600 hertz, which is what I just played, these waves have a frequency of 20,000 years or something like that. So if you were just hanging around waiting for the tone to go by you, you have a long wait. But the universe is very old. So if you take this and play it, compressed in time enormously. That's what the early universe would have sounded like. And in fact, this is Mark Davis, I forget his name right now. Oh, good. Mark Whittle. I actually met him. I went on my wife and I occasionally go on cruises with Scientific American magazine. So you can, if you're interested in this topic, you might want to look at this. You look in Scientific American at the library or whatever, and there's be an ad there from a thing called Bright Horizons or something. And they put lecturers on cruise ships, and you go cruising like everybody else, but you pay extra and you attend lectures when the boat is not in a port. And Mark Whittle was on such a cruise with my wife and myself. And I got to know him a little bit. It turns out one of the professors I worked with at the university in Boulder is a close colleague of Mark Whittle. Mark Whittle studies the acoustics of the early universe. And using this and converting it to frequencies that humans can hear, remember these frequencies are of a scale of 20 to 200,000 years, so you've got to do a lot of manipulation to make this audible. He has written a piece for a choir, and a music professor at the University of Virginia, where he is located. Together, they created a concert where singers sing the tones that were emitted in the early universe, converted to frequencies that humans can hear. And it's fantastic. I don't see a link here. But all the information is here if you want to look this up. Go to YouTube and type in Whittle concert or something like that. And you have this choir singing the sounds of the early universe.
I have a question back to the two bell guys with the sugar scoop.
Yes.
And they were trying to figure out the distortion sounds with the pigeon. What did they ever come up with? That made me think of it. It sounded.
They were listening to the cosmic microwave
That's
background.
what I wanted.
Yeah. Yeah, there was no problem with pigeons or their instrumentation. They were hearing this, they were listening to radio waves that were the first detection.
Or Princeton University.
They were at Bell Labs. The theorists were at Princeton wondering where can we go and get measurements of microwave radiation from the sky, not knowing that 50 miles away, the other two guys had already measured it. So, and then I'm going to close with this picture. Everybody should get this. It's a piece of artwork. This, and it is illustrative of what we were talking about during the break. This is the earliest time in the universe. So you're inside, imagine this in 3 dimensions, you're inside of a sphere, and the light coming to you is, this is the cosmic, the white part is the very high temperatures when atoms didn't exist. Then you have this kind of checkered area, that's the cosmic microwave background. Then you have a dark band, that's the dark ages where there were no stars. Then we have the first galaxies, and the structure or collection of stars into galaxies. Here's early galaxies, modern galaxies, and right in the middle is the solar system. So that, if you imagine yourself at the center of this 3-dimensional version of this, you're inside of a sphere, and all this information is coming to you, including this spiral galaxies, and if you get close to this, you can see that's the sun and the different planets. But this is kind of a way to think about what it's like being on the inside of a sphere of electromagnetic radiation of various frequencies, all revealing secrets. Yes?
What's the white cloud?
This?
No.
This?
Like the Milky
No.
Way.
Oh, there's a dark center, a sort of a white, fuzzy cloud.
Are you talking
around
about
the-
this?
No.
Around
Around the solar system.
Oh, this?
Yeah.
That's the Milky Way.
Oh, okay, thank you.
And this is our companion galaxy providing, that would be like the Large Magellanic Cloud. You know, the Milky Way has 2 companions. Small, not very well-formed galaxies called the Large and Small Magellanic Clouds. And then eventually they're contributing data, or not data, mass to.
Is that connected to Magellan, the explorer?
I think, in the sense that, you know, people like I mentioned Messier, the French astronomer, who went out at night and drew pictures of what he saw. And perhaps Magellan used those as navigation aids. I don't know the history of that. So we have a couple more minutes. Actually, I'll stick around if people have questions, but remember, if you have a really good question, I will save the answer for the entire group when we next meet. But are there any questions right now?
You know, Ed, I have a question.
Yes.
Did the satellites collide over Pennsylvania?
This I do not know. I know they're going to come very
No.
close.
They
But-
did not.
They did not? Okay, well, what happens to all that garbage in space?
It's garbage in space.
Is it gonna go expand with
It's
the universe?
much of it is